Hi, folks at home. Because of COVID and where we are right now with a lot of absences, we're going to take a little detour out of geometry right now and do a little lesson on probability and statistics. So if you're at home, try to play along here. We'll be doing pretty much the same lessons in class. Today's really just about some vocab and some simple ideas within probability. When we talk about the probability of something happening, we can run an experiment. We call it a probability experiment, an action or a trial that has different results, like if we roll a die or we spin a spinner or we choose a card from a deck. The results of those probability experiments, those are called outcomes. When we have a collection of one or more outcomes, that's called an event. And the set of all possible outcomes is called a sample space. So here's an example. Our probability experiment might be rolling a single six-sided die. The sample space would be those outcome numbers, the 1, the 2, the 3, the 4, the 5, or the 6. The event would be something like rolling an even number. What's the probability that you roll an even number? Well, the event would be that you roll an even number. The outcome might be rolling a 4, or rolling a 3, or rolling a 2. So some vocab we'll talk about throughout this chapter. So let's see, a simple example that with two parts to it. So let's say we flip a coin and we roll a die, and we want to list all of the different outcomes that are in the sample space. So the sample space would be all of those different outcomes. So what we use is, we sometimes call this a tree diagram to find those outcomes. We could do this in either order, the die roll or the coin flip, but let's start with the coin flip because the coin flip only has two possible outcomes. You could flip a coin and get heads, or you could flip a coin and get tails. If you flip a coin and get heads, there are 6 different outcomes for when you roll that die. You could roll a 1, 2, 3, 4, 5, or 6. If you roll flip the coin and get a tails, there's also 6 outcomes. So altogether, there are 12 possible outcomes, and that's called the sample space, those combinations. Had we done it the other way, we could have done the die roll first. If I roll a 1, I could roll a 1 and then get either a head or a tail. I could roll a 2 and either get a head or a tail. I could roll a 3 and either get a head or a tail. And if I count those up again, I get 12 possible outcomes. When we talk about probability, probability is always measured from 0 to 1. We can measure it as a fraction or a decimal or as a percent, but it's always between 0 and 1. 1 would mean it's absolutely certain that that's going to happen, and 0 would be impossible that that event is going to happen. If things are equally likely to happen, we could say the probability is 1/2, we could say it's 0.5, or we could say it's 50% that those things were going to happen. Something around 75%, 3 out of 4 times we might say is a likely event, or 1 out of 4 times is an unlikely event. What we talk about, though, is that ratio of things that happen to the total possible outcomes. And that's, we talk about a theoretical probability. What's the probability, the theoretical probability that I flip a coin and I get heads? Well, that theoretical probability, without doing any kind of experiment, we can kind of calculate that theoretical probability, and we do it with a ratio. We talk about the number of favorable outcomes divided by the number of total outcomes. So the favorable outcomes would be like probability I'm going to roll a 5 if I roll a die. The number of outcomes would be there are 6 possible outcomes. So let's talk about this question. Student's taking a quiz and is randomly guessing the answers to 4 true or false questions. What's the probability that a student guesses exactly 2 answers correctly? Exactly 2 correct answers. So before we find out this theoretical probability, we have to know the number of possible outcomes and how many different ways this can happen. So we're talking about a 4-question quiz, and it's true-false, so they're either going to get it right or get it wrong. So let's talk about the number of different outcomes that we can have here. So our correct answers that you guess on your quiz. You might get 0 right, you might get 1 right, you might get 2 right, you might get 3 right, or you might get all 4 correct. And I don't know all those outcomes yet. I don't know how many there are, so let me list them. It's possible that I get all 4 wrong, right? I could get wrong, 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 wrong. I have 0 correct answers. I could get all 4 correct, 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 correct. Or I could get a combination, right? If I get 1 right, I might get the first one wrong and then 3 right. I might get the first one right, the second one wrong, and then the last 2 right. Or first 2 right, third one wrong, last one right, or first 3 right, and the last one wrong. So there are 4 possible ways that I can get 1 right. To get 2 right, let me list those and we'll count them up. So I could get, let's see, right, right, wrong, wrong, right, wrong, right, wrong, right, wrong, wrong, right, wrong, wrong, right, right. I think I've got all the different combinations here. Similarly with 3, the 3 and the 1 are actually going to be the same number of those, but let me list them as well. And I just realized that I said number of correct answers, and I put the number of wrong answers in this column. So let's just to save some time, I'm going to just swap these. This will be if I got 3 right, and this will be if I got 1 right. Sorry about that. All right, so what we're looking at is the number of possible outcomes. So my sample space, how many things are in my sample space? Well, there's 1 possible way to get 0 right. There's 1, 2, 3, 4 possible ways to get 3 right. There's 1, 2, 3, 4, 5, 6 possible ways to get 2 right. There's 1, 2, 3, 4 possible ways to get 1 right. And there is 1 possible way to get all 4 correct. So my sample space would have, if I add those up, 10, 14, 15, 16 items in it. And the question was, what's the probability that this student guesses exactly 2 correct answers? Well, how many ways were there to get 2 right? There were 6 ways to get 2 right. So 6 out of 16, also known as 3 out of 8, is my answer, or about 37.5% chance that you're going to guess right on exactly 2 questions on a true-false question quiz with 4 questions. One of the key takeaways in this section, this is section 13.1 in your book, is this idea of the complement of an event. We talked about complementary angles. They add up to 90. That's kind of a different thing here. When we talk about the complement, that's the probability that something doesn't happen, the probability that the opposite of something happens. We represent a probability, for example, the probability that I roll a 5, I could write as probability of 5. That was that 1/6. The probability that it's not a 5, I would say, is probability of 5 with a line on top of it. So the probability that my roll is not a 5. Well, that's 1 minus the probability that I did roll that 5. It would be 1 minus 1/6. We said that was about 16.67%. It would be 5/6. There's a 5/6 probability that I roll a number that's not a 5. So again, that's called the complement of an event. And the way we write that is the probability of A, the complement of A, because that line is on top, is equal to 1 minus the probability of A, where A is that event that's happening. So this question's asking, if we have 2 6-sided dice that we're rolling together, it tells us there's 36 different possible outcomes, and they've listed them here. We've got a white die and a red die. So a white 1, a red 1, a white 1, a red 2, a white 1, a red 3, a white 1, a red 4, and so on. They've shown us all the different possible combinations of these 2 die. And we can count those up and find out that there's 36 different possible outcomes. So we've got 2 questions here. What is the probability that the sum of these 2 dice is not a 6? Well, what I need to know is, when is the sum of 6? And let me circle those. So I could have a 1 and a 5, a 2 and a 4, a 3 and a 3, a 4 and a 2, or a 5 and a 1. The probability that the sum is 6 would be 1, 2, 3, 4, 5 out of 36. So the probability that it's not 6, probability, I'm going to do this, would equal 31 out of 36. So it's that whole number, that 36 out of 36, taking away those 5 out of 36. What's the probability that the sum is less than or equal to 9? Well, I could count all of the sums that are less than or equal to 9. There's a smaller number that's greater than 9. So if I count those, I've got them circled here in purple. There's 1, 2, 3, 4, 5, 6. The probability that it's greater than 9 is 6 out of 36. So the probability of the opposite of that it's less than or equal to 9, would have to be 30 out of 36. And of course I can reduce those fractions down. That would be 1/6. This would be 5/6. Okay, so probability of the complement is the probability that the opposite of something happens. So we talked about that theoretical probability. That's the very mathematical probability when we know exactly things are going to happen. Sometimes though we do an experiment, and we call this an experimental probability, sometimes things aren't exact. And an experimental probability is based on repeated trials that something's going to happen. And we get that probability based on the number of successes divided by the number of trials. The theoretical and the experimental probability should be close to each other. They're not always exactly the same. So here's an example. We've got this spinner, and you've all spun a spinner before. And it says each section of the spinner shown has exactly the same area. So theoretically, the spinner, to spin a red or a green or a blue or a yellow, each one should be 1/4, right? It should be 25% or 1/4, or 0.25, the probability. But here's what happens as we do this experiment. As we do the experiment, we realize that the red, we spun it 20 times. The red, it landed on red 5 times, green 9 times, blue 3 times, and yellow 3 times. So maybe this spinner that should be equally balanced, maybe it's not so balanced. The question says, for which color is the experimental probability of stopping on the color the same as the theoretical probability? Well, if I'm rolling it 20 times, red is 5 out of 20, green is 9 out of 20, blue is 3 out of 20, and yellow is also 3 out of 20. Notice that those numerators, they have to add up to 20 because we did it 20 times. If I'm a factory maybe that makes spinners, I'm realizing this spinner's not such a great spinner. It's weighted more heavily to land on the green. But the one that comes out to be exactly right, it would be the red. The red has the exact experimental probability that it has the theoretical probability. All right, and one last kind of big word problem here. Our research team is looking at crustaceans. 368 out of 490 crustaceans have ingested plastic. The type of crustaceans that ingested plastic are shown. The team randomly selects a crustacean that ingested plastic to demonstrate their findings. What is the probability that they chose a crayfish? Well, what we need to know is, again, how big is that sample space? How many things are they looking at altogether? And we would find that denominator by adding all of those numbers up. And that denominator, if we add it up, turns out to be 368. The probability that we chose a crayfish would be by putting the number of crayfish in the numerator, which turns out to be, and I know this because I'm looking in the book right now, 21 out of 92. That number's not real important to me, not real useful to me. It's that as a decimal, 0.228. So there's about a 22.8% probability that the crustacean that they chose was a crayfish. Okay, so that's our basic introduction to probability. We're going to do some experiments and play around with these things with dice and with cards and with spinners over the course of the week. And we're also going to look at some two-way tables that sometimes come up in some PSAT, SAT stuff. All right, so that's it for today, guys. Take care. Bye-bye.